when you introduce new materials, you usually enable a new technology. And with a new technology, society changes. It has actually been like this all through history. We go from Stone Age, we started using stones, we went to Bronze Age, we had bronze tools, Iron Age, and so on. And every time this new material came, people got it easier to live and exist and develop, and they got more time to do more pleasurable things. One of the pleasurable things that you actually can do is science. And we scientists have used this to be able now to design materials atom by atom, depositing them layer by layer, and building materials with designer properties. Just think about silicon and semiconductors. It has brought us the transistor, and what has come out is the IT age. We're all connected, wireless communication. It's all in there. And we are still making new materials to further this. But what I'm going to tell you about is something that actually has been around more or less all the time. And I would actually challenge you that you might have made it yourself in kindergarten or preschool or when you use your pencils. Because what graphene is, and what I'm going to talk about, is actually a single layer of graphite. And that's what comes when you do a trace with a pencil. Basically carbon coming out in small molds. Now, that is black. Graphene is not going to be black. But in principle, the invisible part there might very well be graphene. And graphene, of course, has always been there, and it was actually explained with all the super properties by theoreticians in the 40s. But it hadn't been isolated in a laboratory, and you couldn't prove all the amazing properties. And in fact, we usually refer to it as a material of superlatives. It means that it has all these properties, and whatever property you're looking at, it usually is one of the best you can ever make, expect to have. And from the discovery, or the isolation and the proof, in 2004, it took only 6 years until the Nobel Prize was awarded in physics to under Geim and Kostya Novoselov for this discovery. So let's look a little bit at the list of superlatives, or properties. Well, it's a very different material. Every material we know is three-dimensional. It has a length, a width, a breadth, and you can only access the surface. But here you have a material that is only 1 atom thick, or thin. I don't know. How should we put it? It's up to you, right? But anyway, the point is that you can address and functionalize the whole piece of material. And carbon, as it is, made out of, has a special chemical structure that makes it that this mesh, it looks like a chicken wire, this mesh is the strongest material that is around. And it's still flexible. So you have something that is strong, but you can still bend it. So it's a fantastic material in that sense. Also have spectacular electronic properties. It's one of the best conductors. It's the best thermal conductor. And it's also transparent. Actually, a single layer of atoms, as this, only absorb 2% roughly of light. So you can't see it by your naked eye. And now you have this material with all these fantastic properties, and you have all these humans with all their imagination, so of course we'll make nice things out of it. And I will try to make some examples. A few I'll present here. We call this translational nanotechnology because it's down on the nanoscale, and we're trying to move it from us academics into businesses. Let's start with this simple film. I have a piece of graphene with the size of my hand, and I've connected electronically to it. It's on a plastic film. And there is also another film there of a liquid crystal, and that liquid crystal can be turned transparent and opaque, depending on how much current you run through. And what you're seeing there, you either see the logo or not of the University of Cambridge, where this experiment was done. Very impressive, right? But in fact, you could use it as a curtain, and you could. But you don't need to end here. You can go and look at everyday products, and this is a car. It's a concept car put out by Buffs and Daimler, and they actually planned to have graphene in it. They wanted to make the seat heating by graphene, and that's good because you just run current through it and it heats, and it's a comfortable ride. But you can do more. I think if we use our imagination a little bit here, why not heat the windows and defrost them? You can do more. You can do smart electronics in the windscreen. That means that you project all the instrumentation there, and you actually become a much safer driver because the instrumentation is never away from your line of sight. You can do that. Another application of graphene is actually one of the hurdles of electrical cars. And that is that you can make very good batteries that you can charge quickly. That's a major hurdle today. And you can also use them several times. So you could put light, graphene-based batteries into this car. And of course, we would functionalize the roof and make it a solar cell, so we'll harvest from the sun. And while we're at it, why not just build the whole car out of graphene? Because you make very good composites of it, all from a single layer of atoms. And in fact, the first product that ever came out from graphene, believe it or not, was a tennis racket that Novak Djokovic actually uses, where you got good strength-to-weight ratio, and he could smash harder than ever before. These are big things which we are always developing. It brings a better society, and I think my favorite is actually when you go back into the body, and we can functionalize this mesh of carbon atoms, and we can make a mesh of transistors that can light up. And the funny thing with carbon-based materials, and graphene in particular, is that our cells like to grow on it. They can act as scaffolds. And you see in the picture here that you can actually disrupt a cell and send the message via carbon, because that's electrical impulses. And you can make signaling and connecting to the cells. And what the idea here from this German research group was to use this to make an artificial retina. This is a very hard thing to make a prosthesis out of. And what you would do is you say that you have a damaged eye, but your visual cord is still working. And you let it interact with this mesh of graphene transistors. And the impulses will go into the visual center in your brain. And since it has nothing better to do, it will start interpreting these electrical signals as a picture, because this is what it's meant to do. So what you do is, of course, you put a small camera in on your glass, and you project it on this mesh, and you give someone who would be blind some kind of eyesight back. This is a fantastic idea. There are several of them. These things that I've told you doesn't exist, so it's basically what happens. There are many, many applications, and it's basically our imagination that is limiting here. We have to try and see what we can do with this material. It's also a very nice material in the sense we are tapping into an endless resource. Carbon is the fourth most abundant material around us, available to us. And we can make all these things out of it. And we are making things based on something that is one atom layer thick. And to get an idea how much carbon you actually need to use, I think everyone has a picture of a football field. Yeah? Put 3 of them, and you need 10 grams to cover the whole football field. 10 grams, how much is that? I had to check. I went into a candy store, and I looked at the different candies. And my eye caught a Snickers bar, and that's 50 grams. So I can make a technology that basically could functionalize all the windows on a high-rise, for instance, making smart windows, with 1 bite of a Snickers bar. So we're talking about a technology where material will never be the issue. It's just how we can refine it. So what is hindering us today to move forward in this? It's, of course, production. We are very good at making graphene, but we can make it the old way and in small quantities, and in any other way, we are still developing. Now I'll show you a few here. So the initial way was called mechanical exfoliation, or the Scotch tape method. Just 2 pieces of Scotch tape, a piece of graphite, stick it in between, and rip them apart. You get graphite on both, you think which one is thinner, and you repeat 6 times, and then you'll have graphene. Of course, you'll get the best graphene this way, but you'll get a square micrometer, and that's far away from that high-rise. So you need to do better ways. So there are ways being developed all the time, and I have a piece of graphene that I'll show you, and I'll bring it up now. It looks like this. Okay, anyone, how many % of my face vanished when I looked through it? I think it's pretty close to one layer of atoms. It's on a plastic film, though, like this. And in fact, today, by this method, you can make graphene on roll-to-roll productions, and they've made it 100-meter long. So the methods are improving. And in fact, in one way now that we're making it for many developments is basically a kitchen-style method, that you put graphite in solution in your kitchen blender, you run it, and you get high-grade graphene, which you can use for composites, you can use it in batteries, and you can also use it to make touchscreens for the smartphones and tablets around. And this is quite important because, just as we said, there's enormous urge for all these gadgets, and these are usually relying on very rare materials. And if we can replace them with graphene, wow. And there are even some beta models out for these touch phones at the moment. But of course, as we were talking yesterday when we were rehearsing, why does the tablet have to look like that? It could be this, and you can have it interactive. And the picture of the Harry Potter newspaper isn't that far away, because you can functionalize it in many different ways. So by this, I hope I've given you a little bit of flavor that we might be close to a new material revolution. Thank you.